Titans, we have an emergency, and I have a mission for you. I broke my antenna and I can't reach Beast Boy. I need your help.
Wait, does your antenna shoot lasers? Because if it doesn't shoot lasers, what are we even doing?
No star, but it can send radio waves. Very exciting.
In today's episode, the Titans will help design an antenna for Cyborg using actual calculations. And trust me, this will be a fun project. Titans, go!
First we do the center frequency, because the entire antenna design is based on this middle value. So the formula of center frequency design is...
The center frequency is found by taking the square root of the minimum frequency multiplied by the maximum frequency. 30 MHz is multiplied by 300 MHz, and then the square root of the product is taken. This gives a center frequency of 94.86832981 MHz. This frequency becomes the main design reference for the antenna.
That's our main working frequency. Cool, yeah? Oh, so it's like the main frequency of our antenna. Okay, after getting the center frequency, we have to compute the wavelength, since the lengths of the antenna elements depend on it. So we use the formula of... However, this value is theoretical. Real antennas do not behave perfectly because of the material effects, thickness of the conductor, and environmental factors. To correct this, we multiply by 0.94, which is common adjustment used in antenna design to make the measurements more realistic.
Next, we calculate the wavelength. We use the formula lambda equals the speed of light divided by the center frequency, or c over fc. Substituting the values 3 times 10 raised to the power of 8 meters per second divided by 94.86832981 megahertz. Since megahertz means million cycles per second, we converted by 94.86832981 mega times 1 over second. Dividing them together, we get 3.162277766 meters times 0.94. Multiplying them together gets us 2.972541 meters.
So the wave is basically the length of Beast Boy's attention span, spread out.
Our antenna has 3 main heroes. No! I mean parts. There you go.
Next, we find the length of the driven element, where we use the formula LDE is equals to lambda divided by 2. Substituting the values, it will be length of driven element is equals to 2.97541 meters divided by 2, which will give us a LDE of 1.486270 meters.
The driven element is the most important part of the antenna because it is the one directly connected to the transmitter or receiver. Its job is to convert electrical signals into radio waves and vice versa. This length ensures that the antenna can radiate and receive efficiently right after the center frequency, giving us good performance across our whole range.
To get the LD, or length of director, the director must be slightly shorter than the driven element. Now, to get its length, the driven element length, which is 1.48622705 meters, is multiplied by 0.95, or 5% shorter. Now, as we have calculated, this calculation has produced 1.411956975 meters, and there you have it.
Next, we compute the length of the director. The director is placed in front of the driven element, and its purpose is to pull or focus the radio waves in one direction. This increases the forward gain of the antenna and improves signal strength. A typical director must be shorter than the driven element by around 5%. A shorter length makes it slightly capacitive, which helps us guide the waves forward. This director length helps improve the directivity and makes our antenna more directional.
Now we will calculate the length of the reflector. The formula is LR equals 1.05 times LDE. Here, LR is the reflector length and LDE is the driven element. Substituting the driven element, we get LR equals 1.05 times 1.4862705 meters. Multiplying those together gives LR equals 1.5605840025 meters. The reflector must be slightly longer than the driven element.
The reflector is placed behind the driven element, and its purpose is the opposite of the director. It reflects or pushes the energy forward, preventing it from going backwards. To achieve this effect, the reflector must be slightly longer than the driven element. In most Yagi or dipole-based antennas, the reflector is around 5% longer. This makes it slightly inductive, helping it reflect signals properly. And now the solution for the spacing from reflector to driven element. Spacing is also important because even if the element lengths are correct, the antenna won't perform well if the distances between the reflector, driven element, and director are wrong. This spacing ensures that the reflector interacts properly with the driven element to boost the forward radiation. The spacing between the reflector and driven element is based on 15% of the corrected wavelength. Multiplying 2.972541 meters by 0.15 results in 0.4458811 meters.
So in order to get the spacing from driven element to director, we will use the formula of 0.10 multiplied to lambda. The spacing between the driven element and the director is set to 10% of the corrected wavelength. Multiplying 2.972541 meters by 0.10 results in 0.2972541 meters.
Spacing is important because it helps the antenna elements work together properly. Correct spacing gives stronger signal, better direction, and avoids interference.
Lastly, we find the length of boom, where we use the formula LB is equals to spacing of reflector to driven element plus spacing of driven element to director plus 0.0254 meters times 2. Substituting the values, we get 0.4458811 meters plus 0.2972541 meters plus 0.0254 meters times 2. Adding it all up, we get the length of boom is 0.79393525 meters.
That is hero-level engineering.
Good job, guys! You have now made an antenna that can reach me.
Titans, job well done. Today we calculated the center frequency, wavelength, the length and spacing between reflector, driven element, and director. And we also calculated the length of boom. We also created an antenna for sideboard.
Thanks a lot, guys.